What if I told you that chemistry isn't always about a single irreversible transformation? What if I told you that sometimes the chemical reaction can be a living, breathing process, cycling through dramatic changes right before your eyes, almost as if it had a heartbeat? Today we're going to dive into one of the most mesmerizing phenomena in all of chemistry, the Briggs-Rauscher Oscillating clock reaction. This isn't just a reaction, it's a performance. We'll watch it cycle hypnotically through clear, then amber, then a deep, startling blue, only to return to clear and begin its cycle anew. More importantly, we're going to pull back the curtain and understand the incredible molecular ballet that makes this magic happen. To set the stage for this chemical drama, we need to introduce our cast of characters. We have 3 clear, colorless solutions. Solution A contains hydrogen peroxide, our primary oxidizer, and sulfuric acid to keep the pH low and ensure our reactions proceed smoothly. Solution B contains potassium iodate, another powerful oxidizer, and malonic acid, an organic compound that will be crucial for consuming iodine intermediates. Solution C contains manganese sulfate, a catalyst that significantly speeds up key steps. Starch, our iconic indicator, and thiodine, or a similar stabilizer for the iodide. Now let's mix them. As you can see, for a few seconds, the mixture remains clear. Then it suddenly flashes to a brilliant amber or golden yellow. Just as quickly, it snaps to a deep, inky blue-black. And then, just as suddenly as it appeared, the blue vanishes, returning to a clear state, only to repeat the entire sequence. Clear, amber, blue, clear, amber, blue. It's truly hypnotic, a chemical heartbeat. The rhythm might be slightly erratic at first, then settles into a steady pulse for several minutes. So what on earth is happening? This isn't one reaction, it's a tightly orchestrated sequence of 2 competing sets of reactions that dominate alternately. Think of it like a molecular tug-of-war, where the winner determines the color we see. Pathway 1 is the iodide-consuming route that is invisible. The first set of reactions is largely invisible, and it's all about consuming iodide ions. Initially, the iodate from solution B starts reacting with the hydrogen peroxide from solution A. This happens in the acidic environment provided by the sulfuric acid. The net result of this pathway is the consumption of iodide and hydrogen peroxide, and the production of iodine and more iodide ions. Crucially, the manganese catalyst from solution C is essential here, speeding up the oxidation of iodide by hydrogen peroxide. This pathway operates quickly, consuming iodide ions and building up iodine intermediates. This is the reset phase, keeping the solution clear. Pathway 2 is the iodine-producing route, the colors. At some point, the concentration of iodide ions drops below a critical threshold. This allows a second pathway to take over. Here, the iodate begins to react directly with the malonic acid and hydrogen peroxide, but in a different way. This pathway produces a burst of elemental iodine. When a sufficient concentration of I2 is produced, the solution suddenly appears amber. This is the characteristic color of dissolved iodine in solution. However, our solution C also contains starch. Starch molecules have a helical structure that can trap I2 molecules, forming an incredibly intense dark blue complex. So as soon as enough I2 is formed, it immediately binds with the starch and the solution snaps to that dramatic blue-black color. But this blue doesn't last. The very iodine that just formed the blue complex is rapidly consumed by the malonic acid. This is a critical step that resets the system. The malonic acid, acting as a scavenger, reduces the I2 back to I- ions. Once enough I2 is consumed, the starch-iodine complex breaks apart and the blue color vanishes, returning the solution to its clear state. So the reaction isn't just happening. It's oscillating because these 2 pathways are in a constant battle. When pathway 1 is dominant, we're in the clear phase. Iodide is consumed and some I2 is produced, but it's quickly reduced back to I- by the malonic acid, so the solution remains clear. Next, in the amber-blue phase, the concentration of iodide falls too low. Pathway 2 takes over, producing a surge of I2. The solution turns amber, then instantly blue due to starch. The I2 that formed the blue complex is then consumed by the malonic acid, reducing it back to I-. The blue color disappears, and pathway 1 again becomes dominant, starting the cycle over. This continuous consumption and regeneration of key intermediates, iodide and iodine, creates the amazing rhythmic oscillation. It's a perfect feedback loop, a chemical pendulum that swings back and forth, producing its stunning visual display for minutes until one of the reactants is eventually depleted. The Briggs-Rauscher reaction isn't just a pretty visual. It's a profound demonstration of chemical kinetics and non-equilibrium thermodynamics. It shows us that complex systems can exhibit emergent behaviors like oscillation that arise from simple competing reactions. It's a testament to the dynamic and often surprising nature of the molecular world. Next time you see a chemical reaction, remember that it might not be a simple one-way street. Sometimes it's a vibrant cyclical dance driven by molecular forces in a beautifully orchestrated ballet. Thank you for joining me on this exploration of the living chemical.